Hello everyone, welcome to the last episode, episode 7 of Involution series. Today we will recapitulate the ideas we developed up to now and we will solve a problem. We will also provide you a special case of Desargues involution theorem and the dual of Desargues involution theorem. Let's get started. We defined cross ratios for 4 points on a line and then for 4 concurrent lines and then for 4 concyclic points. Later on, we defined involution map. It is a map which when applied twice to a point or a line returns back to itself. Also, secondly, it preserves the cross ratio in one of these 3 configurations. Preserves the cross ratio. For example, when you define involution map from a pencil of line to itself, it must preserve the cross ratio upon application. With these 2 conditions, the function is called an involution map. The configurations under consideration are the 3 on which we define the cross ratio. Well, after defining the involution map, we then proved that any 2 involution pair of points or lines define an involution map uniquely. Suppose if I give you a comma b as one involution pair, that is f of a equal f of b and f of b equal f of a, and then 2 lines such that f of L of LA equal LB and f of LB equal LA. Then these 2 together would determine an unique involution. Not only that, we proved that involution for points on a line is just inversion about a point on the line. That is, you just take a point and assume that as the center of inversion P and then invert all the points about that point P with some radius. So if you just invert all the points on that line, then that is an involution map. And in fact, any involution map can be associated with an inversion about a point. So they are equivalent. So instead of studying involution, we can study inversion about a point on the line. And we also saw its equivalent counterpart for concyclic points. That is, if you had A goes to B and C goes to D, that determines the involution map. We consider AB intersection CD and then let a random line through that point intersects the circle at x and y. Then under that involution, x goes to y and y goes to x. Because we know that 2 involution pairs define an involution. Now, having these properties in mind, we derived the Desargues involution theorem and the dual of it. The Desargues involution theorem states that if you have a cyclic quadrilateral ABCD as shown, and a random line intersects the sides at opposite sides at x1, x2, and other pair of opposite sides at y1, y2, and the diagonals at z1, z2, and the circle itself at w1, w2, it will be true that x1, x2, y1, y2, z1, z2, w1, w2 forms an involution pair. Now, it turns out that if the quadrilateral is not cyclic, even then you can consider the Desargues involution theorem just by eliminating w1, w2 pair. Since there is no circle, you can remove the w1, w2 pair and assert that these 3 forms an involution pair. I know that 2 pairs define an involution and it will be true the 3rd pair will form an involution pair. So therefore, the pairs form involution pairs. And I'm going to strike w1, w2 because if the quadrilateral is not cyclic, you can still apply Desargues involution theorem. The derivation is similar to the actual derivation. Now we applied dual of it. We converted poles to polars, that is points to lines, and polars to poles, that is lines to points. Then that will preserve cross ratio, which was also covered, and hence it will also form involution pair. So for 4 collinear points, they will convert to 4 concurrent lines, preserving the cross ratio. So here is the dual of Desargues involution theorem denoted with DDIT, where you have a tangential quadrilateral with an inscribed circle, and then from any point P on the plane, we consider PA-PC and then PB-PD and then the tangents from P to the incircle and then PE-PF, where E is the intersection of AD-BC and F is the intersection of AB and CD, like the opposite sides. So let's write that down. PA-PC lines and PB-PD lines. As you could see, they are all concurrent, so it forms a required configuration for the involution map. And you have PE-PF and then the two tangents from P to the incircle, call them as L1, L2, form involution pairs. And even here, the quadrilateral need not be tangential. You can extend this theorem, or in fact it's a special case of the theorem where L1 and L2 goes invalid if the quadrilateral is not tangential, which means you cannot inscribe a circle inside the quadrilateral. So leaving out L1, L2, the three remaining pairs define an involution map or correspond to an involution map. As we know, two pairs define an involution, the third one will satisfy that involution map, will respect to that involution map. Let's solve a problem by applying this DDIT and learn from that. So here is the question. You can take some time to think on it and you can attempt it first, try to apply, chase some angles and apply the ideas we developed, and later on you can watch our solution. So the diagram is as shown. You have the triangle ABC and then points P and Q lie on the sides AB and AC such that the circle containing the points AP and Q is tangential to BC at D as shown, and point E is considered such that BD equals EC. And later on we construct the circles BPD and CQD. Call them by omega 1 and omega 2. And let's call the circle APQ as just omega. Extend PD to intersect omega 2 at X. Extend QD to intersect omega 1 at Y. Then prove that points YDEX are concyclic. This is the question. So it is not quite direct. We have to chase some angles and we have to chase some parallelograms as well in the diagram. There are a lot of things going on parallel. For example, BY is parallel to AC. Not only that, DP is parallel to CX. So we will prove them one by one. But when you draw a neat diagram, there is a obvious perk of it. You will get to know some tangential circles or a tangent line of a circle or maybe three collinear points, and something is already evident in our diagram. What is that? The circles omega 1 and omega 2 are tangential at point D. Let's try proving it. So we will reason it out through the tangent chord theorem. Consider the circle omega with APDQ as a cyclic quadrilateral. I know the angle at A is capital A. And the angle opposite to that in that quadrilateral will be 180 minus A, because opposite angles are supplementary. And if this is A, then angle at D would be B plus C. So as the sum is 180. Let's erase A for now. I construct a random line which is not given in the question. I'm just constructing it myself such that it makes an angle B with DP and C with DQ. So now we observe that the angle made by DP with the random line, call it L, equals B, which is also equal to the angle subtended by PD on the arc of omega 1, because angle PBD is also B, right? So by the tangent chord theorem, the line L would be tangential to the circle omega 1, because the angle subtended by DP on the arc equals the angle made by it with the line L. Now same goes for the other side. The angle made by QD with the line L equals the angle subtended by QD on the arc, namely C. So therefore, the line L is also tangential to omega 2. Hence, it is tangential to both omega 1 and omega 2. So the circles are by themselves tangential to each other. because it has a common tangent. This is one of the famous ways to prove two circles are tangents. Alright, having said that, we observe something nice. Since they are tangential at the point D, you can have lot of angle chasing done here. For example, if you consider BYD as theta, then I know that BPD is 180 minus theta. This is 180 minus theta, as opposite angles are supplementary, and therefore the other angle would be theta. And since APDQ is cyclic, I get this opposite angle Q is 180 minus theta. So angle in the other side would be theta. And now it is evident that BY is parallel to QC because of alternate interior angles being equal with QY as transversal. Therefore, BY is parallel to AC. Similarly, it will be true that CX is parallel to AB by same angle, similar angle chasing. And now let's extend BY and CX. Let's say BY intersects CX at Z. As we know, BY is parallel to AC and CX is parallel to AB. We get that ABZC is a parallelogram. Opposite sides are parallel. We first figured out that angle PDQ is B plus C. And by vertically opposite angle, we get XDY is also B plus C. But since ACZB is a parallelogram, we get angle Z equal angle A, and therefore we get that ZXDY is a cyclic quadrilateral because A plus B plus C is 180. So let's write that down. ZXDY is a cyclic quadrilateral. If you try to construct the circle DYZX, it will inevitably pass through the point E. So now maybe we make a conjecture that all points D, Y, Z, X, E are concyclic. So this is what we will be trying to prove. We try to prove D, Y, Z, X, E are cyclic. The points are concyclic because it must pass through the point E. As the question says that dy x E are concyclic, the circumcircle of dyx must pass through E, and it already is passing through Z. Let's get to prove that. First, let us consider the quadrilateral PYQX. This in fact is a self-intersecting quadrilateral. You have the sides PX intersecting with QY. So we cannot use the usual idea or notion of quadrilaterals here. This is a non-simple quadrilateral, PYQX. But why are we using this? You will be fascinated by the application of DDIT, the dual of Desargues involution theorem, over here. We are not going to use a tangential quadrilateral, but still I know the speciality of DDIT for non-tangential quadrilaterals. We have three pairs of involution defined. So let's write them down. For PYQX, from point A, let's take the perspective from point A, the random point on the plane to be A. Then the line joining opposite points from A is a pair. So AP, AQ is one pair, and then AY, AX is another pair. What about the third pair? The third pair will be considered by the line joining from A to the point of intersection of opposite sides of the quadrilateral PYQX. The opposite sides intersection will be PY intersection QX and then PX intersection QY. Well, PX intersection QY is simply D. But what about PY intersection QX? In fact, PY and QX are parallel to each other. The reason is that if you consider this angle, then it will be equal to this angle, which is C, because I know that AC is parallel to BZ. So this angle is C. Hence, by alternate interior angles, angle YBD is C, Therefore, YPD will be C. Similarly, QCD is C by definition. Therefore, QXD is also C. And hence, PY is parallel to QX. But I would say a better way to visualize this is through homothety. If you consider this circle, omega 1, it can be transformed to omega 2 by just a negative homothety with a negative scale factor. You just scale it and reflect about D. You will get this. And this is true for any tangential circles. You can take one circle to the other via a negative scale factor homothety. And when the points that are joined through D are considered, they will be the maps of each other upon this homothety. And hence, PY is taken to XQ upon a homothety map, which means they must be parallel. But anyways, this is just a rigorous way of proving it. A better, like an intuitional way is through homothety. So now, we get that PY and QX are parallel, so they will never meet. So how are we then going to consider the intersection? Then it will be just the point at infinity in that orientation. Hence, that line will just be a line parallel to PY or QX. Let's call that line as small t that passes through A. Alright, so hence PX intersection QI, which is D, should be joined to A. AD and the line T will be the next involution pair. Hence, these three form three involution pairs that correspond to the same involution map, defined by any two of them. Alright, so this is fascinating. Suppose when you consider AB goes to AC upon this involution, a possible involution could be just reflection about the angle bisector at A. Hence, then we look for the angle bisector taking the line T to line AD. Is that true? Let's check it out. I know the angle made by T with AB, say alpha, is same as the angle made by PY with PB, so that will also be alpha, which is equal to angle BDY because it's made by the same segment DY, but BDY equal CDQ, so that will also be alpha. And DQ is a chord of circle omega, the first circle. Hence, if you join A to the point D, the chord DQ shall also subtend alpha by the tangent chord theorem, because BC is tangent to the circle omega and DQ subtends alpha angle with that tangent, therefore it will subtend angle alpha at the circumference. So they are equal. Hence we get angle made by T with AB equal the angle made by AD with AC. So therefore these are isogonal lines, which means they are inclined to the sides in the same angle but in the opposite orientation. So therefore they are reflections about the angle bisector at A. So the angle bisector shall pass through the middle of these two lines, and reflecting the line T about it will take you to AD. So therefore the line T, when reflected about angle bisector, goes to AD, and the line AB reflected about the angle bisector goes to AC. This means the underlying involution is just reflection about the angle bisector at A. So hence AY is obtained by reflecting AX about angle bisector at A. This is the underlying involution, and hence we get that AY and AX are reflections. Now let's erase these. So we will now take to a new diagram. So we got that AY and AX are reflections about the angle bisector. Therefore they are isogonal lines, which means they must make equal angles, say beta and beta, with the sides but in the opposite orientation. Alright, let us join now BY and CX. As we proved that BY is parallel to AC, this angle measures C, that is angle CBY, and angle ABC is B. So the total angle ABY is B plus C. Similarly, the angle at C will be C and angle BCX will be B, as AB is parallel to CX. Therefore, angle ACX will also be B plus C. Hence, we get that triangle ABY is similar to triangle ACX because beta B plus C and the other triangle contains beta and B plus C. This is AA similarity. Therefore, we get BY upon CX is equal to AB upon AC. Now let's extend BY and CX. As we did earlier, they will intersect at a point Z. And since ABZC is a parallelogram, I can replace AB with CZ and AC with BZ. Taking them to appropriate sides, we get BY times BZ equal CX times CZ. So let's see what it says. We have already proved that DYZX are concyclic. We just need to prove point E also lies on that circle. BY into BZ is exactly the power of point B with respect to that circle. Call that circle as gamma. So power of B with respect to gamma, and CX times CZ is exactly the power of C with respect to gamma. Therefore, B and C have the same power with respect to gamma. If two points have equal power with respect to gamma, then they are at equal distances from the center of the circle. This is because power has the form OB square minus R square, where R is the radius of gamma and O is the center of gamma, which equal OC square minus R square, and therefore OB equals OC. And we conclude that point O lies on the perpendicular bisector of BC because OB equal OC. Now, after proving OB equal OC, it means that these two lengths are also equal. Like let's call the foot of perpendicular from O to BC as F. Then FD will be equal to FE because from the points B and C we move equal distances. Therefore, the new position will also be at equal distances from the point F. So we have OF square plus FD square equal OD square, which is also equal to OF square plus FE square, that is OE square. And hence, the value OE will be equal to OD, means that point E lies on the circle, completing our required proof. So this is a subtle way of applying DDIT. You can also think of some other quadrilaterals. You may get some interesting result. Try to manipulate it such that you can apply it to reach the required result. I hope you enjoyed it. We will meet in some other series soon. Thank you everyone. Bye.